Hey guys, so let us have a quick lecture on the next topic, that is the distribution of temperature. Let us begin. So now that we have studied about the controls of insulation, the heating and cooling of atmosphere, let us now look at how this temperature is distributed on the earth, because that is how the climate and will be controlled. So, we all know that the Earth has latitudes and longitudes, and both of these are important as far as the geographic distribution is concerned. So, when we talk about this geographic distribution, we have to keep in mind how this heat is divided. So, we have two types of distribution patterns. One is horizontal and the other one is the vertical. So today we will be doing the horizontal distribution pattern, which in technical language we can call it as latitudinal latitudinal distribution pattern. Okay, now we all know that the earth is tilted. These are a few facts which you need to keep in mind. The first fact is the earth is tilted. Second is that sun is the major source of energy on the earth, and how this energy comes on the earth in form of insolation. This was all we have already covered. So if you look at this diagram, due to this tilt of the earth and these different latitudes, wherein you can see how the angle of the solar insolation or the incoming sunlight on the earth is a major cause for the variation in the heat budget. So we can see here that the latitudes are the most important factor for the distribution, or most important factor which controls the heat distribution. Now, this was known to the climatologists and meteorologists long back, and that is why they named these zones on the basis of the temperature. So, which you can see over here, that from these 23 and a half north to 23 and a half south, which we call as the Tropic of Cancer and Tropic of Capricorn, this zone was named as the torrid zone. Then north of the Tropic of Cancer was the North Temperate Zone. South of the Tropic of Cancer was the South Temperate Zone. And then the poles were regarded as the Frigid Zone. So, respectively, they were known as Arctic Circle in the Northern Hemisphere and Antarctic Circle in the Southern Hemisphere. So, we all are aware that as we go from equator towards the poles, the heat decreases. And what is the reason for that? This is the reason that according to the latitude, the angle of the sun light changes, and therefore the amount of heat budget also, or the temperature also varies. Other than that, you also have to understand that the northern hemisphere and southern hemisphere, they both have completely different distribution patterns. The reason is because the northern hemisphere has lot of land cover in it, while the southern hemisphere has lot of ocean. So the northern hemisphere is also informally known as land hemisphere, while southern hemisphere is known as ocean hemisphere. Ocean hemisphere. So you have to understand a very, very important fact. Of course, I have talked about it in detail in my oceanography lectures, but later on we also be doing it about the specific heat. Specific heat. So the use of, I am sure you all must be knowing what is specific heat or specific heat capacity, and owing to this property, the land, it warms quickly, cools down quickly, while the water, it warms slowly and cools slowly. So this change of the uh, rate of warming and cooling of land mass and the water bodies, it impacts the distribution of heat to a large extent. Okay, so in this slide we have seen a few facts, that is, earth is tilted. The major energy source on the earth is sun, which comes in form of insolation. This insolation varies with latitude, and therefore according to the different latitudes the distribution of temperature is different. Then northern hemisphere has a lot of land and southern hemisphere has a lot of water. Therefore the distribution of temperature in northern and southern hemisphere, they vary, they are not uniform at all. And the last property which we saw here was the specific heat capacity, owing to which the land and water have different rates of warming and cooling. Okay, you all must have come across this term a lot, isotherms. So isotherms, as simple as that, they are lines connecting points with equal temperature. So let us say a person is standing here and another person is standing here on the gradient, or this isotherm of 20 degrees. Both will encounter same temperature. That is why this is called as isotherms. Now why I have given this a diagram of contour lines also. Contours, we all are aware that contours are the lines joining the places of similar height. In this diagram you can see, if I divide this into two parts, on the left hand side you can see that these contours are closely spaced, while on the right hand side they are widely spaced. So what does this mean? That when the contours are closely spaced, then we get a we get a steep slope, while when they are widely spaced the slope is gradual. I am sure you all must have done the profile making exercises, and then you are easily able to understand. Similarly, when we see when we see the isotherms which are closely spaced, it means that the gradient of the uh, isotherms is very steep. So here we can see that they are very closely spaced. So here the temperature gradient will be steep, while on this side they are widely spaced, so the temperature gradient will be very weak. Okay, now an interesting fact over here is that whenever an isotherm map is given, it is not that it is given as such. The temperature values have to be reduced to their sea level equivalents. Now, let us say you are standing on a mountain cliff over here. Someone stands here and he measures temperature T1, while on the sea level, on the sea level, the temperature measured is T2. So in the isotherm map, this temperature will be recorded, not this temperature, because this temperature has to be reduced, means this temperature has to be reduced to its sea level equivalent. Why this is done? Because because it is required to negate or nullify the effect of altitude, because each area having different altitude has different temperature variations depending on the global as well as local factors. So if we are drawing an isotherm map, we simply cannot say that let us say we are talking about some place in Nepal, in the flat terrains and Mount Everest. So, if we are talking about the latitude where Mount Everest is located, we need to reduce that temperature on the top of Mount Everest to the sea level. And how this is done? Say, for example, this temperature T1 is 20 degrees Celsius, and here the height over here, it is say, let us say it is 2000 meters. and the T2 is the sea level. So if we have to get the temperature at this latitude, how do we reduce it to the sea level? We will simply do it because the lapse rate is 6 degrees Celsius per kilometer. So with every kilometer, there is a change of temperature of 6 degrees Celsius. So what do? We will do it as, since we have to bring it down to the sea level, we will do it 20 plus 6 multiplied by 2 kilometers. It becomes 20 plus 12, 32 degrees Celsius. So at this particular latitude, a temperature of 32 degrees Celsius at the sea level will be equivalent to the temperature of 20 degrees Celsius at a height of 2000 meters. So this is what it means, that while drawing the isotherms, they have to be generally reduced to their sea level equivalent to make a uniform map. Otherwise it will be too irregular and too difficult to interpret it. Okay, all right, now these are the two maps which are given, and you have must have commonly come across these maps on the internet, or in the news they might have been showing it. Now these two maps are given for January and July. So why these 2 months? Because in the previous lecture I have already told you that these are the winter months and summer months in the northern hemisphere, and um summer and winter months in the southern hemisphere respectively. So we all know that due to the orbit of the earth around the sun, the elliptical orbit during the months of January, when there is winter in the northern hemisphere, it is summer in the southern hemisphere, and when it is summer in the northern hemisphere, it is winter in the southern hemisphere. This we all know. It means that the distribution of temperature in northern hemisphere during July will be completely different than southern hemisphere, and vice versa. So whenever we have to give the annual mean temperature, it is done on the basis of the temperature distribution during these 2 months uh, in the northern and southern hemispheres. So normally what it is done is that when we talk about this annual distribution of temperature, we have to calculate the mean, and we all know that the temperature is normally the highest in tropics and subtropics, while it is lowest in the polar regions. So this is known to all, which you can see over here. So if you look at this mean annual temperature, you can see that this to this portion, it shows the highest temperature range over here. And then the coldest temperatures, you can see over Antarctica, they are around the minus 40 to minus 50 degrees, while over Arctic, they range from minus 10 to minus 20, while over Greenland, it again comes to minus 40 to minus 50 degrees. Now, you know the reason why that poles they receive the minimum amount of heat, while the tropical regions they receive maximum amount of heat. Another salient feature, if you see over here, in the tropical regions, you can see that these isotherms they are widely spaced. Isotherms are widely spaced in the tropical region. See, even in both the months of January and July, they are all widely spaced. While those in the polar regions or in the higher latitudes over here, if you can see, they are so closely spaced. In the higher latitudes, they are closely spaced. So, what does this mean? Closely spaced. What does this mean? It means that the temperature gradient in the tropical latitudes is very insignificant. You will not notice the change in temperature much, hardly zero point 0.5 zero point 4 degrees Celsius per latitude. But as you go towards the higher latitudes, with change in the every latitude, you will see quite noticeable change in temperature. So that is why the polar isotherms, they are closely spaced. Tropical isotherms, they are widely spaced. Okay. Now, another important thing over here is, if you see carefully, as these isotherms, they pass from the continental part towards the ocean, they do not remain straight. See, they get distorted. Why? Because we have already seen that the due to the uh, uh, variation in the specific heat capacity, the properties of land and water, they change, and therefore when the isotherms, they pass over from land to oceans, they get distorted, they do not remain straight, they are sure to bend either poleward or equatorward, and then they also become irregular. While over once they are passing over the land part, they normally tend to remain straight, they maintain a homogeneous and uniform nature. So this is another property of these isotherms. Now, impact of ocean currents plays a very, very important role in the uh, distribution of temperature. So if you go see my lecture on the surface circulation, surface ocean currents, then there I have talked about two types of ocean currents: the western boundary current and eastern boundary current. The western boundary currents are normally warm currents, and the eastern boundary currents, they are cold currents. So whenever I say eastern boundary and western boundary, what do I mean by that? That the western boundary of ocean, which is on the eastern margin of the continents, and eastern boundary currents, they are on the eastern margin of oceans, while that is on the western margin of the continents. So the warm currents which are on the eastern margin of continents, they also tend to distort, and they cause the bending of the isotherms. So whenever there are colder currents, they will push the isotherms towards the equator. Say for example, if you see here, this is the this is the eastern margin of North America, which is sorry, this is the western margin of North America, which is the eastern boundary of the Pacific Ocean. So over here, what do you see? I'll just erase it and explain this to you once more. So if you see here carefully, this portion, it is the where this laser pointer you can see, this is the western margin of uh, North America, or the eastern margin of the Pacific Ocean. Now there is one current, cold current, which blows, which flows here, and the name of this current is the California current. It is a cold current. So it this cold current comes from the from the poles towards equator. So you can see how these isotherms, they are bending towards the equator. So whenever there is a cold current rushing in, it will normally bend the isotherms towards the equator. Means it this cold temperature comes in and it bends the isotherm towards the equator. Similarly, if there is a warm current, so the warm current tend to bend the isotherms towards the pole. Say for example, in this case, if we see the Atlantic Ocean, where this laser pointer is there, you can see that this is the zone of the western margin of the Atlantic Ocean, but it is eastern boundary of North America. So, and a very important warm current flows here, that is the Gulf Stream. And let me just draw the Gulf Stream for you, and then you will see. So this is the Gulf Stream. So what you can see here, how, and this Gulf Stream impacts up till here. So you can see that these due to this Gulf Stream, the which is a warm current, the isotherms are bending poleward. So this is what you have to keep in mind, that an important fact about the bending of the isotherms. So, when we talk about the seasonal distribution, let us see what are the uh, some facts about these isotherms. This map I have just put it over here to show you that in the northern hemisphere there is a lot of land, while in southern hemisphere there is a lot of ocean or water bodies. So as a result, what will happen? The northern hemisphere, the northern hemisphere isotherms, see, they are very closely spaced. They are irregular. But when we look at the southern hemisphere isotherms, see how widely they are spaced. Close spacing in northern hemisphere during month of January, which is the winter month, and which is summer month for the southern hemisphere, you can see widely spaced isotherms. Now, the isotherms are more symmetrical while passing from continent to ocean in the southern hemisphere. You can see here they're they're maintaining the, see, if they're passing from the ocean to continent in the southern hemisphere, they are more symmetrical, they are not much deflected. But if you see the northern hemisphere, there is lot of irregularity when they pass from the continent towards the oceans. Another thing, due to the cold climate in the northern hemisphere during January, you can see the number of isotherms is more in the northern hemisphere, while the number of isotherms is less in the southern hemisphere. Now, on the continents of northern hemisphere, the isotherms, they on the continental part, they bend sharply towards the equator. So you can see here that these, so in on the North America or Asia, you can see what is the general trend. The isotherms, they are bending towards equator. So what does this mean? It means that the uh, cold polar temperatures, they have sharp impact uh, very close to the tropical latitudes, and that is why they bend the isotherms towards the equator. While the uh, isotherms over the oceans, they are bending towards pole, which means that during January, listen to this very carefully. The poleward bend of isotherms over the ocean tells us that in the month of January, the uh, oceans are relatively warmer than the land masses. Oceans are relatively warmer than the land masses. We will discuss this in detail when we are doing the specific heat capacity in detail. But as of now, you should know that the poleward bend of the isotherms over the oceans of northern hemisphere during January tells us that the temperature of the oceans is more than the land masses. Now, close spacing of January isotherms over continents, you can see here that over the continents they are closely spaced, which means that the temperature gradient is steep over the continents, which proves our point that the land masses are cooler than the oceans. It has been calculated that there is a change of 1.5 degree per latitude on the eastern side of North America and Asia, while on the western side it is 0.44 to 0.55 degree per latitude. Now the ITCZ, the ITCZ, it normally lies south of equator during this month. So this is a line, I will explain this to you in a bit. ITCZ lies south of equator. Sorry for that disturbance. So the ITCZ, it lies south of equator during the months of January, and the warmest latitude lies close to 30 degrees south latitude. I hope you all remember that during January, due to the tilt of the earth, uh, in such a fashion that the northern hemisphere is pointing away from the solar impact. Therefore, the warmest latitude becomes 30 degrees south. While during the months of July, you can see here that the isotherms, they are irregular and widely spaced in the northern hemisphere. Now situation has changed because the northern hemisphere has summers, while southern hemisphere has winter during this month. So what has happened over here is that the uh, northern hemisphere has lesser number of isotherms, while southern hemisphere has more number of isotherms. The northern hemisphere isotherms are widely spaced, while southern hemisphere isotherms, they are closely spaced. And the interesting fact over here is that during the month of July, the high temperature belt, it extends from the North Africa, extends all along the Indian subcontinent and goes towards the Central Asia. And there is another belt of high temperature zone which is in the southwestern part of North America. So all these three belts, they are the result of the uh, differential heating during the months of during the summer month, that is July. Due to this excess heat over here during July, the ITCZ, it now shifts north of the geographical equator. So keep this in mind. So we just saw how the isotherms of January and July, they vary. Now, as July isotherms were continents, see, they bend towards the pole. See, the general trend of July isotherms over continent, it is towards the pole in the northern hemisphere, while that of oceans, it is towards the equator. So this tells us that now the continents, they are heating very fast and they are, you know, hotter than the oceans. That is why this trend. Okay. Now let us take a small detour and let me explain to you what is Intertropical Convergence Zone or ITCZ, because I have been taking this name again and again. ITCZ is also referred to as meteorological equator. Meteorological equator. And how do we identify ITCZ? ITCZ is the zone where trade winds, they converge. Trade winds converge. Okay. So if I am to draw the trade winds on this globe, let me just draw it. So normally we, if we go by simple logic, then the trade winds, they should converge at the equator, but actually it is not the case. The trade winds, they converge at a zone which is either north or south of the equator. Mostly it remains north of the equator during the summer months, while in the winter months it shifts south of the geographical equator. So just for the sake of understanding, if I just draw it over here, if these lines are, if you consider them as trade winds, so this zone, it will be ITCZ. So how do we identify ITCZ in a map or uh, in the globe? Since these two belts, these two winds, they are converging in this zone, so I am sure you all understand that this is a low pressure zone. So these zones are relatively at high pressure from where the wind is starting, and the place where they are converging, it is a low pressure zone. So the low pressure zones are represented by calm weather. Sometimes it is cloudy also over here. Normally they're also referred to as doldrums because here the wind speed is extremely low. Speed is low. Okay, so let me show you a very interesting website from where if you take care, then you can uh, see the daily weather patterns. So right now we are in the winter months. So according to our case, the ITCZ normally shifts south of the equator during the winter months. So let me show this to you. So here, okay, this website is earth.nullschool.net. It's an excellent website. So in this website, if I am to show you the wind pattern, you can see the daily wind patterns over here. But let me first show you how do we mark the ITCZ over here. So let us first look at, yeah, this type of a map. If you see here carefully, then this zone from where my cursor is moving, if you see here carefully, now this zone is the zone where the winds are converging. Let me show this to you. Okay, and let me now start the winds also over here. These arrows, they represent the winds. So first let us look at the Indian Ocean. You can see here that these winds are crossing the equator, and then they are converging with these winds somewhere over here. This is the ITCZ. Right now it is south of the equator over the Indian Ocean. Let us now look about the Atlantic Ocean. Here the ITCZ has moved slightly northward. If you see here carefully, then this is the zone of low pressure where these two wind belts are converging. And if you look over the Pacific Ocean, can you see a fine line over here? Let me just switch it off. You can see this fine line where these wind belts are converging. It means that right now it is the month of March, and due to the slow warming up and the summers coming in, we can see that the ITCZ has moved northward. This is just to arouse your interest that how the ITCZ migration impacts the convergence of the trade winds, and we shall discuss it in detail once we are doing monsoon. Okay, so I hope you will find this lecture interesting. The second part of this lecture about the mean annual temperature and seasonal distribution of temperature will follow soon. Till then, keep on studying. Okay.